Hello and welcome to the lecture series on Equations Reducible to Exact Differential Equation. I am Dr. Geraldina Fernandez, Associate Professor from the Department of Mathematics and Statistics, the Bhopal School of Social Sciences. Dear learners, in my previous module, I have discussed about various rules for solving equations that are of first order and reducible to exact differential equation. So now, in this module, I will be continuing the topic and we will study equations reducible to exact differential equation by rule 3rd. So, rule 3rd states that if in the equation m dx plus n dy equal to 0, we have 1 upon n into del m by del y minus del n by del x. If it is a function of x alone, then for such equations, the integrating factor is given by the formula E integral f of x dx. So, this is rule number 3, by which you can convert a first order differential equation into an exact differential equation by finding the integrating factor with the help of the formula E raised to the power integral f of x dx. So, this is the formula to calculate the integrating factor. So, let us understand this rule 3 with the help of few examples. So, question number 1 is solve y square minus x dx plus 2y dy is equal to 0. So, this is first order differential equation. First step is to write the given differential equation. So, given y square minus x dx plus 2 into y dy is equal to 0. First step is we will mark this as equation number 1. Next step is to compare it with the standard form of exact differential equation, which is m dx plus n dy is equal to 0. So, on comparing the given equation with the standard equation, here the value of m is the coefficient of dx, that is y square minus x, and n is the coefficient of dy. So, here n is 2y. Next step is to partially differentiate m with respect to y and partially differentiate n with respect to x. So, while differentiating m with respect to y, we will get 2y, and while we differentiate n with respect to x, we will get 0. So, clearly we can see that the value of del m upon del y is not equal to the value of del n upon del x. Therefore, which states that equation number 1 is not exact. We have already discussed the condition of exactness for any first order differential equation, that is the condition for exactness for the first order differential equation is that del m upon del y should be equal to del n upon del x. Then only we can say that the given differential equation is exact. But here given equation number 1 cannot satisfy the condition of del m upon del y is equal to del n upon del x. Here we are getting the value of del m upon del y is different and the value of del n upon del x is different, which implies that equation number 1 is not an exact differential equation. So, what we can do? We can convert this first order differential equation into exact differential equation by simply finding the integrating factor. So, and one more condition we have, that is 1 upon n del m upon del y minus del n upon del x. It should be just a function of x, it should be a function of x alone. So, now we will substitute the values and we will see whether we are getting the function of x alone or not. So, 1 upon n here is 2y, 1 upon n is 2y multiplied by del m upon del y. Del m upon del y is what? 2y again, minus del n upon del x is 0, del n upon del x is 0. So, on simplifying we will get 2y divided by 2y, which is 1, which can be taken as a function of x. We are assuming this as a function of x. So, 1 is a constant, we can assume it as x raised to the power 0. So, it can be a function of x. Now, the next step is to find the integrating factor. So, now the integrating factor is given by the formula E integral f of x dx. Here the value of f of x is 1. So, we will substitute the value of f of x, which is 1. So, integration of 1 with respect to x is e raised to the power x. So, this is the integrating factor. Next step is to multiply this integrating factor with equation number 1. So, now we are multiplying equation 1 by integrating factor on both sides. So, equation number 1 was y square minus x into dx plus 2y dy, and we are multiplying it with e raised to the power x on both sides. So, 0 into a raised to the power x is 0 only. So, now we can simplify this and we can write it as e raised to the power x into y square minus e raised to the power x into x dx. We are simply multiplying this e raised to the power x within the bracket plus 2y e raised to the power x dy is equal to 0. We can mark this as equation number 2. Now, equation number 1 is not exact, but by multiplying the integrating factor with equation number 1, we will check whether this new equation, that is equation number 2, whether this is exact or not by the same method. So, now we will again compare it with the standard equation, that is m dx plus n dy is equal to 0. As we have already taken the value of as we have already taken the coefficient of dx as m, so here we can replace it with m dash and n dash. So, here m dash is how much? M dash is y square e raised to the power x minus x e raised to the power x, and n dash is 2y e raised to the power x. Now, again we will check whether equation 2 is exact or not. So, for this we will differentiate m dash with respect to y and differentiate n dash with respect to x. So, while differentiating m dash with respect to y, we will get 2y e raised to the power x. We are differentiating this term with respect to y, so we will get 2y e raised to the power x minus of differentiation of the function of x with respect to y, partially we are differentiating, so we will get 0. So, the final value is 2 into y into e raised to the power x. Similarly, we are differentiating n dash with respect to x. So, while differentiating n dash with respect to x, 2y is treated as constant, and differentiation of e raised to the power x with respect to x will be e raised to the power x. So, we can see that the value this time is same, that is del m dash upon del y is equal to del n dash upon del x, which clearly indicates that equation 2 is exact. So, therefore, we will write equation 2. This implies that equation 2 is exact. As the condition of exactness is satisfied, so equation 2 is exact. Hence, the required solution is given by the formula. Hence, the required solution of equation number 2 is given by integration of m dash dx treating y as constant plus integration of n dash. Now, n dash will have only those terms which are free from x, terms free from x into dy is equal to c, is equal to c. Here we treat x as constant. For the second integral, we treat x as constant. So, now what we will do, we will substitute the value of m dash and n dash. Now, n dash, for n dash we will consider only those terms which are free from x. So, m dash is how much? M dash is, here we have m dash, that is integration y square e raised to the power x minus x into e raised to the power x dx. Here we treat y as constant plus integration of n dash, and it should have only those terms which are free from x. So, here you can see that n dash is not free from x, it is having e raised to the power x multiplied to 2y. So, that cannot be separated. So, here integration, it has no terms, so 0 dy is equal to c. We have a c for the RHS. So, now we will integrate the first integral, and we will have y square is treated as constant, we only have e raised to the power x dx minus, again we can multiply the integral with the terms. So, x e raised to the power x dx, integration of 0 with respect to y will give us one constant, say we can assume it as c1. So, here we have plus c1 is equal to c. So, now for the first term, integration of, as we all know, integration of e raised to the power x is again e raised to the power x. So, here we will have y square, for the first term we will have y square into e raised to the power x minus, then here we have product of two functions. So, we will have to use integration by parts. So, according to Eilert rule, this is the first function, algebraic function is x, and we have an exponential function e raised to the power x. So, x will be treated as the first function and e raised to the power x will be treated as the second function. So, according to integration by parts, first term is kept as it is, integration of second minus whole integration, differentiation of first multiplied by integration of second, and we have a dx, and this c1 can be shifted to the right hand side. So, we have c minus c1. So, difference of two constant can be replaced with a constant again. So, we have y square e raised to the power x minus of, we have a curly bracket over here. So, this is our curly bracket also. So, we have a curly bracket x, integration of e raised to the power x by this formula will be e raised to the power x minus, we have whole integration, differentiation of x with respect to x is 1, and integration of e raised to the power x is again e raised to the power x multiplied by dx, curly bracket is closed. Difference of two constant can be written, can be replaced by another constant, say we can say a, where a is what? A is c minus c1. So, next step we will integrate this e raised to the power x again, and then we will multiply the negative sign with the curly bracket. So, we have the first term is y square e raised to the power x minus of x e raised to the power x into e raised to the power x is equal to a, multiplying this negative sign within the bracket. So, y square e raised to the power x minus of x e raised to the power x plus minus and minus will become plus e raised to the power x is equal to a. So, this is the required solution for the given differential equation. So, question number 2 is solve 5x square minus y into dx plus x dy is equal to 0. So, we have to solve this first order differential equation. So, rewriting the given differential equation, 5x square minus y into dx plus x dy is equal to 0, and marking this as equation number 1. Now, again we will compare it with the standard form of exact differential equation, which is m dx plus n dy is equal to 0. So, now we will compare equation 1 with the given differential equation. So, here we can write the coefficient of dx is m, the coefficient of dy is n. Similarly, the coefficient of dx here is 5x square minus y, and the coefficient of dy is n, that is x. So, next step is to differentiate m with respect to y and differentiate n with respect to x. So, while differentiating m with respect to y, we will get how much? This 5x square will become 0 and differentiation of I with respect to y will become 1. So, finally, we are getting the value as minus 1, whereas differentiation of n with respect to x we are partially differentiating. Here the value of del m upon del y is minus 1 and the value of del n upon del x is plus 1. So, clearly both the values are different. So, del m upon del y is not equal to del n upon del x, which clearly implies that equation number 1 is not exact. So, any differential equation of this form is said to be exact when it satisfies the condition of del m upon del y is equal to del n upon del x. So, if a first order differential equation satisfies this condition, then the given equation is said to be exact. But here the case is different. The given equation 1 does not satisfy the given condition. So, therefore, equation 1 is not exact, but we have a rule to convert it into exact differential equation. So, here we are using rule number 3, and for which we have to find the value of 1 upon n del m upon del y minus del n upon del x. So, now we will calculate the value, and if the result is only a function of x, then we will proceed further to find the value of the integrating factor. So, what is 1 upon n? So, what is n? Basically n is x. So, we will substitute the value. This is 1 upon x. The value of del m upon del y is minus 1, and that of del n upon del x is plus 1. So, minus 1 plus 1, here we have minus 2 upon x. So, which is clearly a function of x. Next, we will calculate the integrating factor. So, integrating factor is given by the formula E integral f of x dx. Here we are using rule number 3. Rule number 3 is only applicable when this expression has function of x alone. So, here substituting the value of f of x, which is minus 2 by x. So, minus 2 is taken out of the integral, and we have integral of 1 upon x dx, which is nothing but log x. So, minus 2 log x. By the property of log, we have a property of log which is n log m is equal to log m raised to the power n. So, we are using this property over here. We have n log m. So, we will have e raised to the power log x raised to the power minus 2. Now, again by the property of log, e raised to the power log x is x. So, here we will have x raised to the power minus 2, which can be written as 1 by x square. Now, the next step is to multiply this integrating factor with equation number 1. So, multiplying equation 1 by integrating factor is 1 upon x square on both sides. On both sides. So, equation number 1 was 5y square. Equation number 1, let me check. Equation number 1 is 5x square minus y. 5x square minus y, and we are multiplying it with 1 upon x square dx, and the next term is x dy. So, we have plus x into 1 upon x square dy, and for the right hand side we have a 0. So, 0 multiplied by any function is again 0. Next, we will simplify this. We will multiply this 1 upon x square with each and every term. Here it will get cancelled. So, what we will have? We will have 5x square upon x square minus y upon x square dx plus 1 upon x dy is equal to 0. So, on simplifying it, we will get, we can cancel it. So, we will have 5 minus y by x square dx plus 1 upon x dy is equal to 0. So, this is our new equation. Again, we will compare it with the standard form of exact differential equation, which is m dx plus n dy equals to 0. As we have already used the notation m and n, so here we can replace it with m dash and n dash. So, we will compare equation 2 with the standard form of exact differential equation. So, here m dash is how much? M dash is the coefficient of dx. The coefficient of dx is 5 minus y by x square, and what is n dash? N dash is the coefficient of dy. So, here the coefficient of dy is 1 upon x. Now, we are repeating the same method again for m dash and n dash. So, here now we will calculate the value of del m dash upon del y and del n dash upon del x. So, let us check whether they are equal or unequal. So, m dash is 5 minus y by x square, 5 minus y by x square, and we are differentiating it with respect to y. And what is n dash? n dash is 1 by x. N dash is 1 upon x, so we are differentiating it with respect to x. So while differentiating it with respect to y, here we have a constant, so differentiation of a constant with respect to y will be 0, and differentiation of y by x square with respect to y will be minus 1 by x square. So final value of del m dash upon del y is minus 1 by x square, and del n dash upon del x by the power rule will give us minus 1 by x square. So here del n dash upon del x is minus 1 by x square. So we can see that both the derivatives are having the same value. So therefore del m dash upon del y is equal to del n dash upon del x. This implies equation 2 is exact because it is fulfilling the condition of del m dash upon del y is equal to del n dash upon del x. So equation 2 is exact. Hence the required solution of equation number 2 is given by the formula remains the same for all the 4 rules, that is integration m dash dx, here y is treated as constant, plus integration n dash, it will have only those terms which are free from x, and the integral is kept as for x as constant, is equal to c is the constant of integration. So now we will substitute the value of m dash and n dash. Here m dash is 5 minus y upon x square, 5 minus y upon x square dx, treating y constant, and n does not have any term which is free from x because n dash is 1 by x. So here plus integration of 0 because we do not have any term, dy is also multiplied over here is equal to c. So simplifying the first term with respect to x, so we will have 5x as the first term minus of y, integration of 1 upon x square will give us minus 1 upon x with the help of power rule. We can shift this c1 to the right hand side and we will have c minus c1. So difference of two constant can be replaced with another constant. So 5x minus and minus will become plus, we have y by x is equal to, we can take it as b, where b is equal to c minus c1. So this is the required solution for the given differential equation. 5x plus y by x is equal to b, where b is the constant of integration.